going to learn about A-theorem things, or were we going to learn about higher dimensions?
Yes.
Cliffhanger will be resolved. So.
It'll be A-theorem things in 4 dimensions. Okay, if we look into 4D superconformal field theory, I mentioned in an earlier lecture that the stress tensor is in a short multiplet. And in some notation, we can write this as so this is the R charge, and these are the spins, and this specifies the shortening condition. And this thing contains at the bottom component the U1R current. And then, maybe I'll write it here. When we act with the supercharges, we get, let's call it S. We get the conserved currents, which give us the supercharges. And then at the top of the multiplet, we get the stress tensor. And if we count the number of operators, there are 4 operators here for the mu index, but it satisfies a conservation law. So I'll write 4 minus 1. And the conservation law is that the divergence of this is 0. And that shows up at level 2. So we have to act with some supercharges to see that. Then here we have this index 4 times 2 for these operators. And then they're their conjugates, so everything I'm going to multiply by 2. But then again, these satisfy a conservation law. So we'll have minus 1 times 2 for the conservation law associated with this thing being conserved, minus another 1 times 2, which is like the analog of the trace of the stress tensor, but for these fermionic components. And then the whole thing is times 2 because there's this one and this one. So here we have 3. Here we have 8, if I did it right. And here for the stress tensor, there are 10 components before we impose the conservation laws, just because this is a 4x4 symmetric matrix. And then the divergence of this being 0 gives us 4 conservation laws in the remaining index. So we have 3 bosonic components, 8 fermionic components, and then 5 bosonic components. So this is some check that we have the same number of bosonic and fermionic components.
10 minus 4 is 6.
Yeah, oh, sorry. Thank you. I'm a little out of breath from so it's 10 minus 4. Yeah, thank you. So 10 minus 4 is 6, and then we also have that the trace of the stress tensor is 0. And so in the end we get 5 bosonic components. Okay, so we can say that this is a 8 boson and 8 fermion multiplet. Now if we look at the non-conformal T mu nu multiplet, then in general what happens is that this R current doesn't have to be conserved. And so we instead of this being 3, we have 4 here. Also here, the supercharges are conserved, but I subtracted another thing, which is like the super partner to this constraint. And so we get, in the T mu nu multiplet, we have altogether, I'll just write the answer. It's 12 bosonic plus 12 fermionic components. And we can write this as the superconformal field theory multiplet plus an extra 4 bosonic and 4 fermionic components. And there's some choice of how to write that. And I'll choose to write it in a way that's called the, that's a chiral superfield. So I'll write it as X. Mm-hmm.
So to go to 12 bosonic components, I've got it's not traceless and the R current is not conserved, but what's 2 more?
That's right, yeah. So the condition, so I'll write it in superspace. I'll write this as, so I'll say d bar, let's write it like this, d alpha. So this is the stress tensor multiplet. And the bottom component is the conserved R current, which I could either write it as, so T alpha dot at the bottom, let's just write it like this, is the R current, which I could write it with alpha and alpha dot index, or using the sigma Pauli matrices, I could write it with the mu index. And this is equal to d bar alpha dot of this X. And so what we see is that in a superconformal field theory, this X would be 0, and then we would get this condition that there's a level 1 null state. So the condition that this thing is 0 is that there's a level 1 null state. Maybe right here also we have d alpha dot boy, what am I doing here? D bar alpha dot of X bar, and this would be d alpha of X. Okay, so and this chiral superfield satisfies d bar alpha dot of X is 0. So this is d bar alpha dot of X bar. This is d alpha of X. And this X encodes the anomalies in conformal symmetry. In particular, if we look at the theta squared component, we get something that's a complex quantity that's, let me just double check my factors, 2/3. Okay, so the top component of this operator is the trace of the stress tensor and the divergence of the R current. The theta squared, the theta components are these components of the basically these are things like sigma mu alpha dot s mu alpha, which are 0 in the superconformal theory. And so Oliver's asked earlier about the counting. There are 2 more components that we have to just add. So this X has an extra 2 components for the bottom component of this chiral superfield, which don't really play a role in this construction because in the end we're taking these derivatives of them anyway. But they play a role in some other contexts. For example, if supersymmetry is spontaneously broken, these things can play the role of the Goldstone fermions. And then the bottom components of X can play the role of some superpartners to them. Okay, so what we see from this, which is interesting, is that supersymmetry relates the breaking of conformal symmetry to the breaking of this R symmetry. And this connection between the breaking of the conformal symmetry and the breaking of the R symmetry led to what's called the multiplet of anomalies. Where we can write down this chiral superfield X as encoding both the conformal anomalies and so for example, X can contain a term which is let's write it like this. X can contain a term which is, for example, some coefficient times S, where S is this glue ball superfield that I wrote down before in the gauge theory. And what's this KRGG? This KRGG encodes the R symmetry anomaly. So if we have here the gauge fields and the U1R current, and if the R symmetry is anomalous, this coefficient is non-zero and we can calculate it. So let's first write it down, for example, in near weak coupling. So for example, well, actually, let me write down first the relation. So now if we look at what this tells us that so T mu is the beta function for 1 over 4g squared f mu nu. This is how the beta function could be written. It's a contribution to the trace of the stress tensor that's proportional to the field strengths. And the divergence of the R current is, let's write down the coefficients that I like. Okay, so this term here is the statement of this triangle diagram. The R current is anomalous. It gets some coefficient that we could read off from the triangle diagram, and it's proportional to FF dual, so that if we integrate both sides of this, this will tell us that the instanton has some definite charge. And this term here tells us that there's the beta function, and then supersymmetry relates them because they're both So these are proportional to the bottom components of S. So the bottom components of S has these terms with the I that we need. and the bottom component of x has these terms. And so if we match what this relation tells us, then we get that.
Top components.
Yeah, sorry, the top components. Yeah, I meant to say the top components, thank you. So we get that the beta function, and I hope I got the factors right, for a pi squared over g squared is this coefficient. There's a 3/2 because of this 2/3 that was over there, times k g r r. Sorry, let me write this better. 3/2 k r g g. Okay, so let's just check this near weak coupling. So near weak coupling, we'll say that suppose that we have some gauge theory with matter fields let's call them Qi and some representations Ri of the gauge group G, then what we'll have is we'll have instanton, we'll have these fermion zero modes for the gauginos, and here I'm just trying to be more general than in the SUSY QCD case, but we could specialize to that case, times T of G, where T is the quadratic Casimir of G of the adjoint. So in particular for SUNC, it's 2NC. And then we have fermion components of these superfields I, and the number of those is the quadratic Casimir of Ri. So this would be 1 for the fundamental of SUN. And so now if we compute this K R G G, this is the anomaly of the R symmetry. And so what we'll do is at weak coupling, the matter fields Qi have dimension 1 at zero coupling. That's their canonical operator dimension. And the dimension of the operator we can always write as 3/2 times the arch charge of Qi. And so at weak coupling we'll assign arch charge 2/3 to, so we get arch charge of Qi is 2/3 in free field theory. Here I mean really zero coupling. And so the arch charge for these fermion components, we should subtract 1, and so we get minus 1/3. And so let's compute the total arch charge anomaly with that charge assignment. We see that the gauginos always contribute 1. And so we have T of G from the gauginos. And now we'll have, with a minus sign, sum over the matter fields I, the arch charge that we've assigned, which is 2/3 minus 1. So I already pulled out the minus sign, times T of Ri. So this is this anomaly that we would compute at zero coupling. And then we could plug that into this beta function. So then we'll get beta is 3/2 times this T of G minus and so for example in SUSY QCD we would get 3/2 this would be 2NC minus 1/3 times NF for the fundamentals and the anti-fundamentals, so we get this extra factor of 2. So this is the 3NC minus NF that we've met before. Okay, so this is the beta function near weak coupling. Now we could try to do the same thing also for general coupling. And so what we could do now is we could say, suppose that we didn't assign this R charge of 2/3, but let's just say more generally, we can take the dimension of QI to be 1 plus, I'm going to call this 1/2 times the anomalous dimension. Sometimes people call it the anomalous dimension, or sometimes 1/2. I'll call it 1/2 times the anomalous dimension. And then I'll set that equal to the R charge, or 3/2 times the R charge of QI. So what I want to do now is I want to say that in general this thing can get some anomalous dimension, and I'll identify that as the R charge by the same relation between operator dimension and charges. Now with this R symmetry I could plug in and get K RGG is, so again I just read it off from the same instanton diagram. The gauginos still contribute T of G, and for the matter fields I have plus sum over the matter fields. The number of them is, the number of their zero modes is T of Ri, and then for their R charge I should solve for this R of Qi and subtract 1. So let's write R of Qi is 2/3 times so this is R of Qi, and now I'll subtract 1. So this, because we subtract 1 for the fermion R charge.
Sorry, are you supposed to subtract 1 from the whole thing?
Yeah, let me just do it now here. So R of Qi I'm going to take to be 2/3 times 1 plus 1/2 gamma I, and so R is minus 1/3 plus 1/3 gamma I. So actually let me, thank you. I think I had a typo. Let me redraw that. So we can write this as minus 1/3 times 1 minus gamma I. Okay. Okay, so if we write down what we get from this, we get that the beta function of 8 pi squared over g squared is equal to 3/2 times that. I hope I copied it right. And in particular, if we're at a 0 of the beta function, so we can write beta of 1 over g squared is minus 2 g cubed beta of g. And that should be 0 at a fixed point. So at a renormalization group fixed point, we have to impose that this thing in the parentheses is 0, which is the statement that we have a conserved U1R symmetry. Now, actually, in general, now we can ask if we should believe this away from the renormalization group fixed points, and it's not clear whether the answer is yes or no. But I'd like to advocate that we can trust it away from the renormalization group fixed points, and actually, this is proportional to what's called the exact NSVZ beta function. And the difference between this and the NSVZ beta function So NSVZ had a similar argument for an exact beta function, and their argument led to something which is some function of g squared times this one that I wrote up. That's just right, the beta that we get from up there. And this thing is related to some scheme. And in general, if we're away from the fixed point, then we have to worry about scheme ambiguities and things like that. And so I won't make too big of a deal about what these things are away from the fixed point. The main point is that at the fixed points, this thing should vanish. The thing in the parentheses should vanish. Okay, going back to X, so suppose that we're in a superconformal field theory. So the superconformal field theory has X equals to 0, and so in particular we should be at the 0 of this beta function without backgrounds. But now, following, I guess this was Nadi's third lesson yesterday, we should turn on background fields for all of the symmetries. And so we could turn on background fields, and then we find that the background fields lead to non-zero X. So if we go back to here, we again have a multiplet of anomalies, but now instead of X being some dynamical field in the theory, now we can have X having contributions related to the background fields. So for example, if we have a global flavor symmetry, then X can be violated by the background for the global flavor symmetry. So the X has a component which is the R symmetry, and the R symmetry will be anomalous in the background of the global flavor symmetry. So now I'll just edit this with, instead of the gauge symmetry, we have some flavor symmetry. These are background fields now for the flavor symmetries. And now here, instead of S, we'll write down the analog of this S for the flavor symmetries. So maybe I'll just write it out. Why don't I just write here S for the flavor symmetry? So here S for the flavor symmetry is the same kind of expression, but now these are the flavor charges. And now we could look in components what that means. So now we have K of R flavor. I should have just kept that formula. So this is the same formula from before, but now these are for the flavor symmetries, the background flavor symmetries. And this is the 't Hooft anomaly coefficient. And what about the trace of the stress tensor? The trace of the stress tensor also gets a contribution proportional to F mu nu, but we don't interpret this as the beta function for the gauge coupling. What it actually is, which is related to the beta function, the coefficient of the gauge coupling if we would have gauged it, is the coefficient of the operator two-point function. So if we look in a conformal field theory, the flavor current let's say this is at some point x, and this is at some point 0. This is uniquely determined by the Ward identities up to some overall normalization. And so I'm going to call the overall normalization tau. I could perhaps write down the formula. It's like tau flavor. There's some factor of 2 pi to the 4th. I'll just write here some ... This is fixed by the symmetry. Maybe I should write it. Okay, maybe to avoid rushing later, I won't bother to write out the components. But this is something that's completely fixed by the flavor symmetries, and there's this coefficient, and we get that T mu mu is this same coefficient, tau ff over let's see, tau ff over, I think, maybe 8 pi squared. This needs to be checked. The correct formula is that, so again, these are related by supersymmetry, and what we get from this is that the two-point function of these currents for flavor symmetries is -3 times the KRFF. So maybe I should just say a little bit about the normalization that I chose here. So if we look at an example of a free chiral superfield, so for example, let's say that we have some superfield phi, then there's a U1 symmetry that rotates the chiral superfield phi. So we'll assign it 1 under the flavor symmetry.
Earlier, when we had arc symmetry, we could have written this equation as theta theta component of x is equals to theta theta component of s up some factor. So is it the same factor that we are getting in this?
It's the same factor.
Is your
Yes.
question?
Yeah, so the question was if these normalization factors are the same as for the R symmetry. And so the relative normalization between these two just follows from the normalization in S between F mu nu, and FF tilde. And that's what leads to this relation. So what I'm doing now is to just do a check that this is the right relation. So I could keep track of all the factors of pi, but another nice way to do it is just to check for a free field case to make sure that I have the right normalization. So I'm going to check this final answer just for the free field case. Yes, thank you. So for example, for a free chiral superfield with charge 1, then it has U1R charge two-thirds, because that's the free field value. That's the statement that has dimension 1 for a free field. And so then if I compute this triangle diagram for the 't Hooft anomaly with the R current and the flavor current and the flavor current, there's the fermion component of this that runs in the loop. It has R charge, so this is KRFF, and we get a factor of minus 1/3 because we subtract 1 from here, and each one of these flavor pieces give us 1, and so we get minus 1/3, and I'm normalizing this tau FF in this case to be 1 in this normalization, and so this is equal to minus 3 KRFF. So this is so the upshot of this is that if you have a conserved flavor symmetry and an R symmetry, you could compute this 't Hooft anomaly, and then that gives you the coefficient of the current 2-point function in the conformal field theory. Any question? Okay, another background that could be turned on in a conformal field theory is a background metric. And that's how we see the A and C conformal anomalies. So we can turn on curvature. So we consider this theory in a curved spacetime. And we could also, because the metric couples to the stress tensor, we're turning on a background fields for the stress tensor multiplet. And the stress tensor multiplet, in addition to containing T mu nu, it contains also the R symmetry. So in addition to turning on the background metric, we could turn on background U1R gauge fields. And then what was found, this was found in great paper by Anselmi, Friedman, Grisaro, and Johansson, what they found is that there are two terms, and the two terms correspond to the fact that there are two conformal anomalies, A and C. So there's one term which is the C anomaly. Let me just write the coefficients. So C over 24 pi squared W, this curly W squared, and this curly W squared is analogous to the W that we have for gauge fields, but this is for the gravity, and so this W, its bottom component, is the gravitino. It's some spin 3/2 object. So this is some, again, we're writing things that are chiral superfields. So this is a chiral superfield. And then there's another term that gives the A anomaly. And this is some other object that I won't really spell out, but that's formed, that if you want, you could check in their paper. But what it is it's some superfield version of the Euler density and the Pontryagin density. And that's what A is. So if we look at what this tells us for T mu mu, so again, T mu mu with a 2/3 plus I d mu is X top component. So we could look at the top component of this X and see what it gives us for the conformal and the R symmetry anomaly. And so we get T mu has the expected terms. It's C over 16 pi squared. I'm just going to write C squared for the Weil tensor squared, some contraction of the Weil tensor squared that you can form from the Riemann tensor subtracting the traces, minus A over 16 pi squared times the Euler density minus C over 6 pi squared this is the background field strength for the R symmetry. And here, this anomaly term here for the background field strength for the R symmetry, it's similar to over here, that if there's a contribution to the trace of the stress tensor involving some background field strength squared, that coefficient is a 2-point function of some current. So that tells us that the 2-point function of the U1R current is proportional to the anomaly C, which makes sense because the stress tensor 2-point function is also proportional to C. So this C also enters in the 2-point function of the stress tensor. And so in particular from this we get that in this normalization, the 2-point function of the R current is some normalization factor that's 16/3 times C. And now we can look at how to relate this to the R symmetry. So now the triangle diagram, instead of being KRFF, it's, let me go right here. So we get, maybe I'll write this as some covariant derivative in this background. D mu J R mu is C minus A times R twiddle. So this gets contributions from both of these terms, the C and the A terms. And R tilde is like the metric version of FF dual. Plus 8 over 27 FF dual. Okay, so this is what we get from just taking the theta squared component of this side. And now we can identify these terms as 't Hooft anomalies. So this term is related to this coefficient here tells us that K, let's just say with one R, this is associated with a triangle diagram with the R current and two gravitons. Let's just write T mu nu, T mu nu. That's what leads to this kind of anomaly. So you can have an anomaly in the U1 current where it couples to the metric, and that's what leads to this RR dual. And so that tells us that this coefficient is related to the 't Hooft anomaly that we calculate from this triangle diagram. This is the anomaly that I would just call trace U1R. So that's that term. And then this term is what I would call trace U1R cubed. It tells us that if we turn on a background field strength for the R symmetry, there's a divergence of the R current, and that's trace U1R cubed. And the upshot of all of this is that A in a superconformal field theory can be written exactly as 3 over 32, let's just write trace of R cubed for the U1R symmetry. And okay, so these are the exact expressions in the superconformal field theory for the A and C conformal anomalies in terms of the R symmetry anomaly, 't Hooft anomalies. So again, a great thing about this is that these 't Hooft anomalies satisfy the 't Hooft condition that they're constant along renormalization group flows. So by using this, we can compute the exact A and C anomalies in superconformal field theories. So as an application of this, so maybe I should say that there's an A theorem that we could check, which is that and that there's an argument by Komratgatsky and Schwimmer for this based on if you spontaneously break conformal symmetry, you have a dilaton, and you can relate the difference between AUV and AIR to some dilaton scattering total cross-section, which has a positivity requirement. So let's just write here, Komorgotsky and Schwimmer. And this was first conjectured by Cardy. And so we could check it for different cases. And so let me write, I usually get tired of writing the 3 over 32, and so I decide to change my normalization to drop the 3 over 32. So maybe I'll just already do that now. So we'll forget about that 3 over 32 factor. And so let's compute it for instance, these SUSY QCD in the conformal window. So we have SUSY QCD where the theory in the ultraviolet is asymptotically free, and then in the infrared we get some superconformal field theory. And we could compute A both here in the ultraviolet and A in the infrared. Uh-huh.
So in the expression for the trace arc cube, is that missing pi squared in one?
Yes, definitely. Yeah, this must be pi squared. Let's see, where did I copy it down? Yeah, I think I wanted to probably just divide this by let's just write some number times pi squared. This should definitely be divided by pi squared because that's the thing that integrates to give the instanton density. So thank you. Yeah, in the end, the final formula is correct, but the intermediate steps might have some typos. Okay, so let's compute this A without the 3 over 32 factor for SUSY QCD. So let's compute A is this is the normalization that I'll use. And so I'll write this as the contribution from the gauginos. So when I look at these different contributions, there will be a contribution from the gauginos. And the gauginos, I could read it off from a diagram like this. We have, so the gauginos contribute 1. So we basically I'm just going to sum the R charges. I didn't mean to say that diagram. We just sum the R charges cubed. So for the gauginos, they have R charge 1, and so we get 3 minus 1, so that's 2. So we get 2 times the number of gauginos. So I'll just write that as the dimension of the gauge group. And now plus the contribution for the matter fields. And so there's 2 times NC times NF matter fields. And they have some R charge. And so let me write here A1 of R. Where here A1 of R is just the contribution to this anomaly, and so it's 3. So R would be the R charge for the scalar component of the chiral superfield. So I subtract 1 to get the contribution from the fermions. So this is just some cubic function of R. So A, let's write down the different cases. So A in the ultraviolet is 2, the dimension of the group is NC squared minus 1 plus A1, and we'll evaluate it in the ultraviolet at R charge 2/3. Because again, R charge 2/3 is the free field value. So that's A in the ultraviolet. And now A in the infrared is, the only difference is we have a different R charge for the matter fields. So we'll have 2 times the same function A1, but now we'll plug in the anomaly-free R symmetry that was on the table for the past 2 days. The previous 2 days. 1 minus NC over NF. That was the anomaly-free R symmetry. And now we can check that this A in the infrared is less than A in the ultraviolet. In fact, if we look at this function A1 of R, so if we just plot this function as a function of R, so it's some cubic function like this, and it has a local maximum at 2/3. Has a minimum at 4/3. This free field value here is 2/9. So for the ultraviolet, this A1 is at this local maximum. So this is where we are in the ultraviolet. And now as we go to the infrared, we get this value of the R charge. This is the anomaly-free R symmetry. And we can see that this value of the R symmetry is less than 2/3. So we move somewhere down here. So this is in the ultraviolet, and this is in the infrared. And so along the renormalization group flow, this R charge changes from the free field value up here to this interacting value down here. The fact that it's on this side, if we go back to this formula that the R charge of Q is 2/3 times the dimension of Q. This tells us that we have some negative anomalous dimension here. Which is true. Like when you look in gauge theories, you get some negative contributions to the anomalous dimension. So we can see that A is decreased because this part here stays the same, and then the contributions from the matter fields are kind of going down this hill. And we could think about going down this hill as being like the renormalization group flow between the ultraviolet and the infrared. Up here at the top, we have anomalous dimension 0. And then as we go along the renormalization group flow, the anomalous dimension increases because the gauge coupling is flowing. And then eventually we hit a conformal field theory where the R symmetry is conserved. So that makes sense, because if we think about this multiplet of anomalies where x theta squared is equal to times the divergence of the R current. The non-zero beta function that's associated with this tells us that the R symmetry that's in the same multiplet with the stress tensor actually isn't conserved. And so when we're up here at the top of the renormalization group flow, let's say here we're in the ultraviolet, and here we're in the infrared. Here we have an R current which is in the same multiplet with the stress tensor, which is assigning R charge 2/3 to the matter fields. And that R current is JR conserved. We can write as the conserved piece plus something that's proportional to the axial anomalous current. So this is J for the anomalous current, mu. So the R current where we assign 2/3 is the conserved one that we talked about plus this anomalous piece. And this anomalous piece isn't conserved, and so that gives us the non-conservation of this, which is related to the trace of the stress tensor. Now, if a current is conserved, it can't have anomalous dimension, and so this thing has exact dimension 3. If it's not conserved, it has to have a positive anomalous dimension by unitarity. So this thing has dimension 3 plus something. So this has delta equals 3, and this has delta equals 3 plus positive. And so the fact that this is a higher dimension operator than this tells us that as you flow to the infrared, this thing flows to 0. So this is how we could interpret the renormalization group flow, is that this anomalous piece is flowing to 0, and then here at the bottom we just get JR conserved. And so that's these flowing R charges that I was trying to interpret over there earlier. Now, we could write this more for the more general case, for general matter content. For more general matter content, our condition, let's see, is it still here? Our condition for conformal field theory is that X, when we turn all backgrounds to 0, should be 0. And that tells us that the R symmetry has to be anomaly free. So we had this condition that plus sum on I So this was the condition that the beta function should vanish, that the R symmetry should be conserved. And this is one condition on these R charges. And so in general, this might underdetermine the R symmetry, because we have one condition on the R symmetry. And when it underdetermines the R symmetry is if the R symmetry can mix with other flavor symmetries. And so if it can mix with other flavor symmetries, those flavor symmetries are also anomaly free. And so then the R symmetry would be underdetermined. So often conserved. U1 flavor symmetries. And so here it was mixing with the anomalous symmetry, which flows to 0, but in general it could also mix with the non-anomalous conserved U1 symmetries. And then in that case, there's a way to determine which is the right R symmetry. So the superconformal U1R in the T mu nu multiplet has a property that it locally maximizes this A of R this combination over all conserved UNRs. So if there are many different possible conserved UNRs, the correct one is the one that locally maximizes this function. And the argument for this is that we could, in general, we could take the R symmetry to be some, let's say some choice of some base R symmetry, let's call it R0, plus some linear combination with a flavor symmetry. So these are what the charges would be. So this is some coefficient that we'd like to determine. And so the statement that it locally maximizes this function is that if I take a derivative of this with respect to R, I get 0. And so I can write this as 9 trace of R squared F. So I'm just taking derivative with respect to R. Actually, I'm taking derivative with respect to S. And so then I get this F minus trace of F. And this thing turns out to be 0 for the superconformal R symmetry. This is something that you can show from the word identities. Sorry?
Does F have to be central in the flavor for them? No.
So the question was if F has to be central in the...
Yeah, like so is it a U1 factor or is it just any?
Yeah, so this is for any flavor. If it's not a U1 symmetry, then you still have to impose this condition, but it's not that interesting. It's only a non-trivial condition if it's a U1 symmetry, but for non... So we could have applied this, for instance, in SUSY QCD. We could have applied it also to the SU and F left and SU and F right flavor symmetries. We could have also applied it to the baryon number symmetry. And so these conditions would tell us that we should choose our R symmetry to commute with all of those symmetries. Yeah, so this is true for any flavor symmetry. So and the reason why this is true is related to another multiplet of anomalies for this flavor current. If I take this flavor current d bar squared of J flavor, then if the flavor current, so the flavor current sits in a chiral superfield, and if it's a conserved flavor current, this should be 0. If it's a broken flavor current, this is something that's like a chiral superfield because we've already acted with d bar squared, so another d bar is going to give 0. And what you get is that this can have a contribution from the gravity multiplet, which is this W squared times some coefficient, which is related to K R flavor, K R R F. So this is some 't Hooft anomaly involving the flavor symmetry and the R symmetries. And there's only one term that you can write down here. You can't write down the analog of this other term that I wrote in this case. And so there's only one term, and that tells you that the 't Hooft anomalies are linearly related, because this thing here contains both the gravity piece and the R symmetry piece. And so this tells you that there's a relation between this 't Hooft anomaly involving gravity and the 't Hooft anomaly involving the R symmetry. Okay. Let's see. Maybe I should stop and ask if there's a question. Huh?
This condition that you've obtained so far is just for extremizing A. Where is it important that it has to be a maximum?
Okay. Yeah. So the question was, where is it important that it has to be a maximum? Yeah. Thank you for the question. So we could see that it has to be a maximum because if I take here two derivatives with respect to s, so I'll get. So if I think about this as a function of s, I'll get d squared. So s is this parameter where I'm mixing with the flavor symmetry. Then I'll just take one more derivative, and so I'll get 18 trace of R times FF. So here I just take another derivative, and that replaces this with an F. And this trace RFF was minus 3 times tau FF. Or minus 1/3. Yeah, so R would be minus 1/3. Yeah, minus 1/3. So this is equal to 6 with a minus sign, and where this tau is the 2-point function of the flavor current. And so that's 0. Or sorry, that's tau is positive, and so this is negative. So the second derivative is negative. So it's a local maximum.
So 1 minute passed, so maybe we should finish up.
Okay. Yeah, so maybe just to finish up, I'll say that, so for instance, if we go back to this function, what we're doing in general is we're maximizing, locally maximizing on this function subject to some constraints. So for example, in the free field case, there are no constraints, and so we just get here is the local maximum. Now, for instance, in SUSY QCD, the constraint is that the R symmetry has to be anomaly free, and so that pushes us down this hill. So in general, we could also write down a function where, along the renormalization group flow, where we impose those constraints with Lagrange multipliers. This was pointed out by David Kutasov. And then we can get something that looks like a decreasing A function in this case, that flows between the ultraviolet and the infrared. And then we can try to connect that to the stronger versions of the A theorem, that you can write down a monotonically decreasing A function whose derivatives, this A function can be constructed, if I had a little bit more time I would write it down, it could be constructed in such a way so that its derivatives with respect to the Lagrange multipliers that are imposing the constraints are proportional to the beta functions, because the constraints are that the beta functions should be 0. And so by construction, the derivatives with respect to these Lagrange multipliers give the beta functions. So that tells you that the beta functions can be related to the derivatives of this flowing A function along the flow. So if people want to hear more about that, I could discuss it outside of the lecture. Yeah, maybe just because I can't resist mentioning a couple of other quick consequences. One consequence of this is that the R symmetry is always an algebraic number for superconformal field theories. That's what this suggests. So this suggests that the R symmetry is of the form like n plus because when you maximize this cubic function, you're solving some quadratic equation. And so you get some R charges, which are algebraic numbers. And then that also implies that the A and C are also algebraic numbers. And also these two-point function coefficients of currents, they're all algebraic numbers. And as far as we know, that we haven't seen a counterexample to that. But so this is some property of n equals 1 theories, is that these things that you can determine exactly have this very special form. Maybe I'll end with that.
So this is to say there's no pi, or so pi equals numbers. This is algebraic.
That's right. Yeah. So for example, the point was that, for instance, pi can't be here. So we can't have like an anomalous dimension of some operator, as far as I know, in a superconformal field theory, that's some number like pi or, yeah. Yes?
How robust is the negativity of this anomalous dimension in gauge theory? Is that like a perturbative statement?
Okay. Yeah. So the question was how robust is this statement about the anomalous dimension being negative in gauge theory? Yeah, you can check perturbatively that it's true, and actually, if I had a little bit more time, I was going to do the case where you flow from asymptotically free SUSY QCD to its free magnetic dual, and there you see some interesting properties with the accidental symmetries acting the free magnetic dual. But the thing that reminded me about this is that in the magnetic dual, there's this operator phi that appears in the superpotential. And this operator phi is a gauge invariant operator, and so it gets positive anomalous dimension. So it's actually moving in this direction, whereas the Q's are moving in that direction. And so then to check that the A theorem is satisfied, it requires a little bit more work. But and there are also cases where phi can cross this boundary and go down to this branch, which leads to some funny behavior.